Hello, everyone. Thank you for attending. So today I would like to talk to you a little bit about teaching introductory statistics. I have a few different aspects I will touch on, and I won't go into all of them very deep. They're often really more intended to provide you with food for thought, and everything that I bring up in this presentation, you can continue to research on your own and find additional sources and examples. So one of the goals, what I'll talk about next for the next few minutes, I will talk about the goals that have been identified in the GAISE report for introductory students. That is, when we teach an introductory course, often in the syllabus, you have to state your learning objectives or your learning goals. And in the GAISE guidelines, there are exactly 9 specified. The first one, and probably most important one, is that we train our students to become critical consumers of information. And I found this example just on Monday. So some of you might have seen this already, but when I saw it, it was kind of hard to believe. So the state of Georgia had made a bar chart of the top 5 counties with the greatest numbers of confirmed COVID-19 cases. And when you look at the bar chart, you can see there's clearly a downward trend. What happened is, if you look very closely at the x-axis, you see that the dates are out of order, and that what appears to be a clear downward trend in recent days actually is not going down that chronologically. When you resort the dates and put them in chronological order, you'll see somewhat of a bump. Still a downward trend, but with additional bumps in between. Okay, so I'll go back to my slides. So in addition to critical consumers, the second goal for students in introductory courses is that we want to teach them the idea of an investigative process. An investigative process that allows us to answer research questions that we're interested in, that allows us to figure out what is the right type of data that requires to be collected to answer that research question. And sort of what I always consider the most important thing, one of the most important things coming out of a statistics class, is that given a research question, can the student actually identify the correct procedure, the correct statistical procedure to analyze the data and to actually get the answer to the originally posited question. Graphical displays and numerical summaries, students should be able to produce them. But in addition, also to interpret them. And especially when it comes to the interpretation, it's not just what you can see in the graphs, it's also often what you cannot see, what your graph does not display. In addition to, or what's goal number 4? Goal number 4 has to do, or obviously addresses, variability, and this idea that variability in the data really underlies pretty much everything that we do in statistics, any associations, any modeling relationships of variables. And for students to understand variability takes always time to develop throughout the course. It is something that you really have to stress over and over and over again, especially when you have students that for the first time take an introductory course. It's really, I cannot overemphasize how hard that idea of variability actually is for students. The central role of randomness. What is a random sample, a simple random sample? What are other types of sampling that are adequate? Sometimes you need certain types of sampling given your research question, and you may need ideas, sampling ideas like cluster sampling or stratified sampling. And randomness is something that I believe students underestimate. Students always think they can judge if something has been random or not. And if you ask students to randomly pick 6 numbers between 1 and 49, and you analyze these data from your students, I've done this multiple times in my classes, you will see that the first number they pick usually is somewhere between 1 and 5, and then the second number they pick is somewhere around 10. And so you can see this chronological order where they actually are increasing the number they choose as they go. So one moral of the story, and there is actually a publication with this, is that us as human beings, we are terrible at being random or assigning things randomly or judging randomness. Okay. The last 4 goals include statistical modeling. Again, this ties back to variability, that we can describe variables through distributions, and that distributions are considered a statistical model. Once we have an understanding of statistical models, statistical inference is often what we consider the final goal in a lot of introductory courses. And the last 2 are kind of 2 goals that you really start teaching or implementing from day 1 as you try to work through the other goals, namely trying to teach students how to use some basic statistical software and that students can use and interpret and draw conclusions from basic output. And last is, what are ethical issues associated with sound statistical practice? And for ethical issues, I have some slides at the end. Again, this is also something that you can't overemphasize enough, how important it is for students to kind of make that, or to raise that awareness from the very beginning of the semester. Okay, I have another picture. So if I go into presentation mode, will you see the picture now?
I do.
Okay. Okay. So as I was looking for some examples to illustrate some of these goals, I actually came across a website or a blog, and I found this type of blackboard chart that I thought summarizes very well how data is often being misused. And I think this is something you can bring into the classroom, and you can find examples for each one of them. But one that's often kind of missed, but very frequently actually does appear in the media, is that when you consider, for example, a percentage change in combination with a small sample size. So effects can look a lot larger than what they really are in terms of the absolute numbers, let's say, perhaps. Data fishing is also something that increasingly becomes more important because we increasingly have larger and larger data sets. We collect more data. It's fairly easy to have or to gain access to large data sets. And if you look long enough, you'll find something. So that's always a consideration that I teach my students, that you start with your presided research questions. You know the type of data you need to collect. You look at the variables that you need to answer those questions. And then that's what you rely on to get an answer for your research question. Misleading data visualizations. You should have seen a picture of, or an example of one a couple minutes ago. Faulty polling, flawed correlations. And for flawed correlation, I do have an example. This typical example of correlation is not causation. So this example is also taken from the same blog. It was just a neat example, and it is a different example than usually what you find with the ice cream and the sharks, let's say. So among all the things that can show this correlation between the increase in car accidents in June in the state of New York and the increase in bear attacks in the month of June in the state of New York, it's most likely that the correlation really is only by chance. And so illustrating students what it means, correlation, what can be the reasons for the correlations, and that chance is really one of those. Next, I'm going to talk a little bit more about the new emphases that were included in the GAISE revision. And the first one is teach statistical thinking. And as part of teaching statistical thinking, we want to teach statistics as an investigative process of problem solving and decision making. Ultimately, we want to use the data we have, the evidence that we find in the data to make a decision. And important in statistical thinking is obviously also that we don't just look at one variable at a time. Although introductory statistics very often starts out with just one variable when you introduce graphical displays, numerical summaries in the very beginning. Even inference is typically introduced using one variable. It becomes pretty clear that without accounting for additional variables, we will never see the full and the complete picture. And one thing I would like to add to these new emphases is to actually embrace statistical interpretations. And I think the two most important interpretations in introductory statistics classes are concerned about p-values and confidence intervals. And those are two concepts that intro students will struggle with. It's very hard to kind of let students, or that have students, get students to the point where they actually appreciate the interpretation of a p-value, namely that it's really measured on a continuum. It gives you the strength of evidence on a continuum. And we've seen this in recent months or last year where we've had this discussion about, should we even, how should inference look like? Because very often a lot of scientists live and die by literally their significance levels. And if they have a p-value at the end of their study that's just barely below the significance level, everything is good to them. And if they have a p-value that's just barely above, then they failed, in their opinion, providing the evidence, when really that's not the case. It's really sort of coming back to this idea of what probability means. And in addition to that, p-values are only one piece of the evidence. There's a lot of additional evidence in your data that should help you make a right or proper, I would say, a proper and adequate decision. For example, how were your data collected? What was the design of the experiment? And were the right variables collected and analyzed, the right methods used? So along with the interpretation of a p-value is also then this idea of practical versus statistical significance. We can have statistical significance just by sheer volume of data, whether a change, let's say, that we're looking for is even practically significant, you really can only assess by looking at your effect size. And your effect size, you can estimate properly with uncertainty using your confidence intervals. So at the end of an intro stats class, in terms of interpretation and statistical inference, what I would like for my students to have taken away and it's an ambitious goal, is that they feel comfortable with p-values, they feel comfortable with confidence intervals. And that's a hard hurdle to get over. So talking a little bit more about the second one, that was this investigative process of problem solving and decision making. What I always use in the classroom, or what I found myself to be as a statistician, is really more like, I consider myself a data detective. I like to solve puzzles in the sense that when we have a research question, just this idea even, what type of data do you have to collect? And what variables do you have to collect? And in which way do you have to collect these data? And that's really important sort of to make your students aware of, because at the end of the day, as a statistician, the way they will use it is most likely as a scientist or as someone with more expertise in the subject matter, and then collaborating maybe with a statistician to get the answers to their research questions. And this communication piece between expert in the subject matter and statisticians, it is very essential, because I can remember a good number of consulting experiences I have where researchers came to me and said, this is what I want to analyze, here are my data, this is my research question. And then as I was starting to dig into the data, it became very obvious pretty quickly. They had collected the wrong type of data. They didn't have sometimes enough data. And so it's incredibly, it's a process that evolves throughout your consulting experience, where it's hard to underestimate, again, to say how important it is to communicate clearly what is the question that you would like to answer and how do we do this best. There are two facets to problem solving. One is at the level of the research question, and the other is at the data level. And the data level is always interesting in an introductory class, because at the data level, what can happen is you can have contamination in your data. That's very likely. You can have what's considered an outlier. Data properties, do you have ordinal data? Do you have continuous data? And then do the data satisfy the necessary assumptions for the research methods that you have in mind in terms of applying? So for data contamination and outliers, and I'm gonna, given the time, I'm gonna skip this next example. I'll take a look at the outliers. So at the data level, do you drop an outlier? Do you not drop an outlier? Of course, to us, we know exactly what the right answer is. But to students, that's not as obvious. Students would like to drop an outlier because it just doesn't fit with the rest. It messes up their analysis. And they think often maybe it's just a wrong measurement, a mistake in the data collection. And I think one of the best examples to illustrate that outliers can be very, very informative and very useful is the discovery of the ozone hole. And that discovery was really delayed by many, many, many years because NASA collected data using a satellite, and they were getting these observations that were just too small. They considered them outliers and they were automatically removed. And so the conclusion for many years was that the ozone layer is still stable. And it really took an in-person expedition to the Antarctic to finally verify these low measurements, and which consequently led to the discovery of the ozone hole. Another example for an investigative process of decision making is for example, let's say a company is interested in buying a new spam filter, and there's a 30-day free test trial, and they have figured out that the software will pay for itself if less than 5% of all the mail that are classified as non-spam actually turn out to be spam. And so there are a ton of questions that you would have to answer answer the question reliably. For example, well, how many messages should you test? Whose messages should you test? Are there people in the company that are more prone to spam mail than others? What's your strength of evidence? And one thing that I like about this example is that you really can use it nicely to illustrate type 1 and type 2 errors. Namely, well, what do we do about the rate of messages that is incorrectly labeled as spam? What value is associated with each of the mistakes? And data, so my last example in this data level, addresses data properties. And so this is also an example I got from students not too long ago. This was a graduate student who studied survey data on a Likert scale. And so obviously her data were ordinal. And she wanted to find out if there was a significant change from pre to post treatment. And out of all the data, out of all the participants in the study, she had 27 for which she had complete pre and post data for all the survey questions. And the question that I got from her was, while my data are ordinal and they do not follow a normal distribution, should I use the Wilcoxon signed rank test? Or can I actually use a t-test? And that goes back to the central limit theory and students feeling comfortable enough making such decisions. You know, we often say we give these guidelines, like if you have a sample size of 30 or higher, that's just a number. It really depends on the original distribution of your data. And so when in doubt, what I advised the student to do in this case was, well, 27 is actually a pretty good sample size. And I told her to look both at the Wilcoxon signed rank test and the t-test, here a matched pairs t-test, and to compare the results. And in the ideal case, the results qualitatively will be the same. So they both will either reject or fail to reject, sort of having a similar magnitude in their p-values, not obviously exactly the same, but hopefully close. And actually that's exactly what happened. So for all the tests that she was looking at, for all the questions, whatever we found with the Wilcoxon signed rank test was confirmed or is the same that we found with just using a matched pairs t-test. Okay, so multivariable thinking. I think it is important to address this in an introductory stats class, even if it just means introducing students to this idea. So we will never really be able to understand the entire picture of the complex associations in some phenomenon that we're trying to study without looking at several variables at a time. And whenever you have more information available that actually does include information, you just improve your signal to noise ratio. So again, you have to be careful when you have multivariable or multivariate data. And it doesn't always turn out to be the case the way it looks, let's say, when you just look at your numerical summaries at first glance. And the IRIS data are a perfect example for that. The IRIS data actually consists of 5 variables, and the measurements include the sepal length and width and the petal length and width, in addition to the species. And so students are always prone to crunch the numbers and to look at the numbers. And when I most recently used that example in class, that's exactly what my students did. They just looked at the numbers. And what we see here are positive correlations that are very strong, but we also see a few negative correlations, sort of like moderate strength. Well, when you look at a scatter plot matrix that sort of gives you a picture of the bivariate relationships between the 4 variables, you can see that that's really the case. You have positive, stronger positive relationships, and you have a few that look a little bit negative. But to you, with a trained eye as a statistician, you probably already recognize or realize that there are some clusters in the plots that have the negative relationships. And when we take the last variable, the species, into account, and we use the species, we color the different species, then you can actually see that all the relationships, regardless of type or species, they're all positive. So accounting for often sort of categorical variables in your data often has information that goes at the detail of the exact relationships that you don't cover when you just ignore the type of information when you have different groupings of observations in your data. An example that I thought was fun, or I've used in the classroom that is fun for students in introductory classes, is I asked them once, well, what do you consider to be the ideal height of your spouse? And they'll give you, and I asked them to report their own height and then the ideal height. And they did this, and I collected the data, I entered the data, and when you plot the data, again, you see a negative relationship. It's kind of like the taller you are, the shorter you want your spouse to be. And students really were puzzled by that. And just as an example a moment ago, well, you have to account for gender. Once you actually accounted for gender, which was the 3rd variable I had collected, then again, you get the relationship that you were expecting to. And that's a sort of easy example you can implement in the classroom. You can use SurveyMonkey, or in the lab even in JUMP, let's say, you can collect data fairly easily and analyze it and have it for the students to analyze. So in many introductory courses, we introduce simple linear regression, and then we kind of stop there. And not all students will continue and take a second course in regression, but some will. And what happens in the second course is we teach them about multiple linear regression models. And I'm an advocate for sort of introducing students to the potential or to the power of a multiple linear regression model already in the intro class. Not to make them understand or learn any technicalities, but just to illustrate them that, again, in real life, we'll have to most likely look at more than just one variable. And there's a really neat example that was provided by Mendenhall and Sinkic in their course, a second course in statistics regression analysis. And I just love this example for being real data and how it actually worked out in terms of the gain you get by including a second variable. So the data are on the auction price of 32 antique grandfather clocks. And the auction price is the response. And then for each of these grandfather clocks, they had information on the age of the clock and the number of bidders that were present at the auction. And so when you fit the variables individually in JUMP, like 2 simple linear regression models, then you see that age actually explains a good chunk of the variability. The number of bidders in the room, not quite as much. So you have one model that has a little bit more than 50% of the variability explained. The other one can add something. The question is, how much does it add? And so what happens when you combine both the variables into a multiple linear regression model, you will actually get a tremendous improvement in your model that is more than I would have expected. You come up with almost 90%. So remember, the one was 53%, the other one was 15%. 90% is quite an increase. And the second reason why I like this example is this is an example where the interaction term is actually fairly reasonably easy to explain, and students usually will catch up on this, what it means to have an interaction in this case. And if you include the interaction, it turns out that the interaction is highly significant, and you get your model up to almost 95 or more than 95% of the variability that the model can explain. And so this is just really to show or illustrate students the potential, what we can do when we consider more than one variable at a time. Applicability of the GAISE guidelines, they're not just meant for introductory courses, for your first one. They really apply to also classes that go beyond introductory courses. They are written in a way that they apply to all types of students, majors, statistical literacy versus methods, all learning environments, whether you have face-to-face instruction or online or some hybrid. And also they're written in a way that make them suitable for instruction at the university level down to the high school level. So the GAISE guidelines, if you get a chance, if you start a teaching career here shortly or soon, I would highly recommend to read through them, to read through the goals, the recommendations. Alan Rossman on last Friday talked extensively about the recommendations. And while the GAISE report itself is fairly long, over 100 pages, if you chunk it, you can actually chunk it nicely and look at the goals and the recommendations, and that gets you somewhere around 20 pages. And then you can read the other parts of the GAISE report at different times. Given the time that I lost here, unfortunately, a little bit, so just food for thought. How do we assess students? And one fundamental thing to keep in mind is when you want to assess your students is keep in mind the level that you teach at or that you taught at in your class, and what's the level you're assessing at. And for the most part of your assessments, you want those two to ideally match up reasonably well. And if you haven't had any experience with assessments, which as a graduate student, if you're lucky, you get to teach an introductory class, maybe under supervision, but you most likely will not have to have written exams or assessments. And if you've never written an assessment or an exam before, check out Bloom's taxonomy. Actually, it's the revised taxonomy, and it really sort of categorizes a student's understanding, a student's learning into 6 different categories. The lowest just simply being able to remember information. And the most advanced or the highest level of learning when we are able to create new knowledge based on the knowledge that we have. And there is a nice, when you look at Bloom's taxonomy, there are a lot of charts out there, and they sort of give you ideas of how do you phrase a question that gets at the level of understanding or that gets at the level of applying? And what would I have to do sort of to get at the level of evaluating that I can test if a student can evaluate the evidence that is in the data. And then in an introductory course, I've gotten to the point of evaluating where I was giving a question and I think my students should be able to evaluate the evidence. I have not really included, let's say, creating new knowledge in the assessments in the introductory level. But again, it's really just intended to serve as a reminder. If you're new to teaching, look into it and think about how you write your exams before you give them. So this is an example I have that to me falls into the category of evaluation. That's what I was just talking about. And so I give students the context, I give them all the information, and without going into the details, there are two operators, two possible decisions. And I ask them, well, which one do you agree with? What would you decide? Who's correct? And students really have to look at the data and see that this is about variability, sampling variability versus variability in your original data. And so if the student really got to the understanding that I hope they would get, then they would realize that considering the sampling variability, that was the right way to go, and that the operator who, in this case, argued that this manufacturing process was was no longer on target, that is the operator who was right, because you had to consider the sampling distribution and not just the individual variability. Last, what I would like to mention is ethics. And I think ethics are very important to talk to our students about. And this is something that you actually can let them sort of find out on their own if you give them a homework or a side project. I introduce my students to what's called retractionwatch.com. And what's interesting is that, one of the reasons for why a lot of manuscripts or publications do get retracted are related to data fraud and data manipulation. They make up a decent chunk of part of the retracted manuscripts. One example here is this Dutch social psychologist who actually ended up fabricating entire data sets that he gave to his students to earn their PhD. So they were completely separated from the data collection process. And I mean, it's hard to kind of understand what's going on in someone to actually fabricate entire data sets. Depending on the crowd that you have, there's a really nice video from the show last night with John Oliver. And he talks about science studies and how science actually is often portrayed in the media, like when there are findings from scientific studies, how will they interpret it, let's say, in the newspaper? Or what does the media turn these scientific findings into when they report them into the media? And the video is about 20 minutes long. It's quite funny. It does have some explicit language, but it actually drives home a lot of the things that we talked about today here. How do you collect your data? Do you have a sufficiently large sample size? What is practical significance versus statistical significance? One thing he brings up is, well, who is the sponsor of that study? So that you often have this bias, and that it's not surprising that when industry sponsors studies, that the results that come out of these studies are often sort of delivering a message that benefits the industry. And I think that's there are some good real life examples in there, and I think most students will find it entertaining. And I think that puts me out of time. So I will make my presentation available. And I, again, apologize about the mishap with the slides. So with that, thank you. Any questions?
There are a couple questions if you wanted to answer them before I come on, Ulrike.
Let me go back into
I'll
Zoom.
read them to you.
Oh, yeah.
So there was some like mixture of comments and questions kind of related to the content that's in a course that is kind of following these guidelines, and some questions about, you know, do you get to chi-square? How do you get past the basics that the students struggle with and still have time to talk about some of the more advanced things that are, of course, more interesting to us anyway? And where would you introduce multivariable statistics in such a course?
So I have introduced multivariable statistics typically at the end, although most of us have made this experience that at the end of the semester, we try to cram in what we really have to get to. So it's not always the ideal time. In terms of, let's say, chi-square tests, or do I introduce multiple regression? At Iowa State, we have four different, actually more than four. We have several introductory statistics courses, and they're geared towards the individual audiences. So I know chi-square testing goes into the course that's offered to the general audience in the College of Liberal Arts and Sciences, where you have, for example, a lot of social science or psychology majors. But it is not being introduced in another section that we have, which is primarily for business students. In that section, we do simple linear regression, and this is where I would definitely go to multiple linear regression and use that as an example of multivariable thinking. Does that answer the question?
I think so, and they were all similar. I think they all go into that same pot.
Okay.
All right. So I will get started. Let me share my screen. Okay, well, so this is the second bit of the workshop, and this time we're going to be focusing on teaching introdata science, and I titled this The Art and Science of Teaching Data Science, mostly because I've been kind of interested in making art while doing data science. So this is not my artwork at all. This is by Thomas Peterson, actually, who is the core developer for the ggplot2 package, but it is generative art made in R, and I enjoy playing around with it, and I really enjoy the visuals. But at the same time, we are going to be talking a little bit about both the art and the science of doing this. So we've heard quite a bit about the GAISE guidelines, so I'm going to give you my very brief annotated reading of it to motivate it. So teach statistical thinking comes first, and when I think about the word statistical thinking, I'm thinking it's not a commonly used subset of tests and intervals and how to produce them with hand calculations. I think statistical thinking is something a little bit more than that. The guidelines also talk about relationships among many variables, and that means multivariate analysis, meaning we need to use computing. Now, that doesn't mean you have to write code per se, that particular guideline, but it does mean you need to use some sort of computing. It also says use technology, and I think about technology as not technology that is only going to be applicable in the intro course or that doesn't follow good science principles. I think especially for teaching data science, we can push ourselves to kind of align with what folks who are doing data science are actually using. And finally, it says analyze data. And yesterday in Hillary Parker's keynote, we also saw the I think she called it the notorious data science cycle. And it is not just inference and modeling. It includes those, but it's also data importing, cleaning, preparation, exploration, and visualization. And we've heard in quite a few talks so far this idea of actually teaching the entire cycle, which means we have to teach this nitty-gritty as well. So when we think about this, I feel like a course that satisfies these 4 points is looking a little bit more like today's intro data science courses than stats courses, but that's not because intro stats is bad for you. Like, there's no such thing. I think it just means maybe it's time to visit intro stats in light of emergence of data science. But I think right now we're at least living in a land where we have these intro data science courses, and they are distinct mostly from our intro statistics courses. So how might we design one of these? So here is one possible design for an intro data science course with 3 modules, 3 big units to it: exploring data, making rigorous conclusions, and looking further. So in the exploring data stage, we start with data visualization. But we use that to actually teach statistical concepts like confounding variables and Simpson's paradox, and also use that time of building these data visualizations to introduce our students to a toolkit. So the course that I would propose for an intro data science course, and the one I teach, uses with RStudio. Everything is done as in our markdown document from the student's side, and also they use version control with Git. So this is the time when they start getting introduced to it bit by bit. Then we take a step back and say, okay, we've visualized these clean data sets, but that's not usually how they come about in nature. So what if we take a step back and start thinking about how much data tidying we might want to do, recoding, transformation, and also getting data. And when we say getting data, there's the statistical concepts of data collection that we go over, but also computational concepts like web scraping and iteration and collecting data from many, many web pages, for example. There's also a teamwork component to all of this. So this is when students start doing work in teams and using GitHub as a collaboration tool as well. Next, we get to the statistics topic, and that's the making rigorous conclusions topic. And we start with modeling, and in fact get to multivariate models pretty quickly, visualizing these interactions and doing prediction as opposed to doing inference on these models to begin with, and also just baby introduction to machine learning with prediction and validation, mostly to say this is how machine learning is tied to these things you're learning about, and you might be interested in learning more about it at a later course. And simulation is, inference is also introduced at the end of this unit via simulation. The idea being that if students are enthusiastic about this topic and are going to be taking more statistics courses, they will have maybe a more traditional introduction to inference motivated by the mathematics behind it in a course that has the appropriate mathematical requirements and probably a probability theory requirement as well. But there's no way to, I think there's no reason to try to get all of that information in here in the first course, because you end up running out of time or end up having to put prerequisites on the course. And finally, for the last couple of weeks of the class, let the students breathe is what I think. But what that means is teach them some stuff that they're not necessarily expected to be assessed on per se, but use that time wisely to introduce them to important topics while at home, instead of doing homework, they are working on their final projects. So this is where, some of the topics are optional, but I would say one that is not is data science ethics. So I'll give some examples about how to introduce that. But 2 topics that I like introducing here are things like text analysis and kind of baby Bayesian inference, but with and then focus on things like communication and dissemination for their projects. So what does this actually look like? We said we start with visualization, so let's try to put this into practice. So you are going to be invited into my day 1 of my class now, and this is how we start things. So I'd encourage those of you who have the energy at the end of the day to visit that link, bit.ly/rscloud-ecots2020. And it will ask you to log in. If you have used RStudio Cloud before, you might already have a login. If you have a Google or a GitHub account, you're welcome to use those as well to log in. Otherwise, it will ask you to create an account. And I know that some of you may have landed at that link already, but I'll keep talking for a second only so I can walk you through the next steps if you want to listen for a few more seconds, and then we will definitely have time to pause and go through it yourselves. So once you land into this workspace, you're going to see some projects listed, and we're going to start with the first one titled UN Votes. This is an example that I like to use in my first day of class because we'll take a look at the data in a second. And once you open that project, when you click Start and open that project, you're going to see in the Files pane, so you can see this highlighted on my screen here, an R Markdown document with the extension RMD called 01-UN Votes. And if you open that and then click on Knit, you should see a document get produced. You might see an error. That's not an R error. That's your browser, which might be trying to block pop-ups telling you, do you really want this pop-up? And you can say yes, try again, and you're going to see a visualization like this produced. So I'm going to give you a second to get to that point, and I'm going to do it myself as well, and then we're going to get to the very last bullet point here. So let me go to my student persona here, and I've landed in this workspace. I think the link is in the chat if you have missed it from my slides. And so this is launching an RStudio project. And so the nice thing about this is that we haven't had to do any sort of installation. So your students really can, roll into class. Well, I don't know, maybe they won't be rolling into class next fall, but can roll into however you're meeting them. And they can get started doing hands-on data analysis without getting stuck at the installation stage. Nothing like technology to slow you down when you're talking. All right, so let's go ahead and take a look at this. And what I've done is I've opened the R Markdown document, and I'm going to knit this document. So this data set, the nice thing about this data set is that it is voting in the United Nations by many, many countries. I will be honest with you, I am contemplating swapping out this example potentially for a COVID example for next year, but holding off for the time being to see what that might be like. I think that session earlier about using COVID data was really nice. But one thing about an example like that, or the COVID example, is that people can find some sort of connection to it. So here they're finding the connection with their countries. So once the students knit this document, the goal for them is just to scroll down and take a look at this visualization where we're seeing data about how the countries have voted over the years and on various issues. So arms control and disarmament, colonialism, so on and so forth. And I have particularly chosen 3 countries: US, Turkey, and the United Kingdom and Northern Ireland. I'm living in the UK right now. I've lived in the US for many years, and I am originally from Turkey. So these are countries that I have some sort of connection to. One of the things that a lot of people will recognize when they first look at this visualization is how Turkey's voting on an issue, say like Palestinian conflict, differs very much from the US, and also that it maybe looks like the opinions have changed around the year 1960. But if you think about it, we have no idea what these resolutions are about, what these votes are. So this is just a percentage of yes on the y-axis. Yes could mean pro one side of the conflict or the other. We don't really know based on just the data that we have here. So what we want the students to do, having learned no R or no computing whatsoever so far, is to look in this source code in this R Markdown document, locate where Turkey appears, and replace that with a country of their own choosing. So I'm going to give each of you a little bit of time to do that. My sister lives in France, so that's what I'm going to put in, and I'll need the document. So what an exercise like this allows us to do is students get to bring in something about themselves to the class. So at this point, what I would usually ask students to do is turn to the person next to them, or I don't know, put in a chat box what country they chose and why. And that's actually an icebreaker activity if you think about it. It's usually, I am from that country, or I've been there, or I studied abroad there, or something like that. And then they've actually produced a data visualization. And we were able to do this within a few minutes of me starting to talk. And this is, I think, a great way to start your class as well, getting your students to do things that they are going to be doing. And an example like this is not just a toy example, it is a real data analysis example. And just like any real interesting data analysis example, it does actually take quite a bit of code to get through. So at this point, instead of trying to teach all this code on first day, that would, I think, be a ridiculous approach. What we want to do is tell the students, look, we're able to recognize something and make a change to it and create a new visualization. So you have actually coded so far and done a little bit of data analysis and done a bit of interpretation. And what we're going to do is over the next few weeks, we're going to teach you what this all means. And then usually I like revisiting this exercise a few weeks into the class, and they can look at this again and say, oh, okay, now I understand what a group by is, or a summarize is, so on and so forth. So this is what the class starts with. Then where do we go after that? So I've kind of structured this in 3 parts into the 3 questions that tend to keep me up at night. What should students learn? How will students learn best? And what tools will enhance student learning? So let's start with, so these basically map to content, pedagogy, and infrastructure. So we're going to start with content. And what I'm going to do is I'm going to walk you through 3 case studies. And each of the case studies are going to be bookended by an example from real student projects. So I think one of the best ways of assessing whether students have learned something like that is, were they able to apply it in an open-ended project, so you can see what they have gathered from what we've learned. The first case study is a case study about money in politics. So this is a web scraping exercise from the website opensecrets.org. I like this website because, you know, politics is something students tend to be interested in. And money in politics also is, I think, an interesting topic. And this year I was teaching not in the US, but in the UK, and it is a US-based website. But one of the things I was able to find there was some data on foreign connected PACs. So these are foreign companies donating to US businesses. So there is actually a foreign connection to it as well. So what do we do here? We have on this website, at first, what the students are asked to do is, from the 2020 election cycle, take a look at this structured data, this table, and let's get that data into R. So they get to learn about web scraping, a little bit of text parsing, because there's some text elements here, like $signs and commas, that are going to make our data character strings as opposed to numeric data. They learn about data types, so character, numeric, so on and so forth. And they learn just an introduction to regular expressions. You can see that in the second column, country and parent company are kind of squeezed into a column separated by these slashes. So we need a way to extract out this country information so that we can use that later. Then we say, all right, we've done this. So we've spent some time scraping data from this single page, but we have this many, many pages with the same structure. So let's learn to write functions and then iterate it over these pages so that we can get data from all of the election cycles. And ultimately, they do a data visualization. So here, what we've asked students to do, as I said, I'm teaching in the UK right now, so we subsetted the data for PACs that are connected to the UK, and then plotted how much money has been donated or donated to Democratic and Republican campaigns. This is and then they get to interpret what they're seeing here. So they make a data visualization and interpret it as well. And this is the kind of insight you simply couldn't get from browsing around the website, because you need to be able to get all this data into a data frame and subset it the way you want before you can see that, well, up until 2010, contributions to both parties were increasing, but after that, the Democratic contributions from the UK have started decreasing. Another thing we talk about here before we go through all of this is a little bit of data science ethics. Just because you can get data out of a website doesn't mean you should. The first thing you should ask is, am I even allowed to? So we start talking about how web crawlers work and whether or not a robot is allowed to scrape a website. So there's a function for doing that. But we also start hinting at, even if you're allowed, is this the sort of data that you think is ethical to scrape or not? So after having gone through this case study in the class, here's an example from one of the teams from my class. So this was Team Fried Egg Jellyfish. And they wanted to ask the question, is there a north-south divide in the UK? In terms of university satisfaction. So they found this website that has data on student satisfaction about universities. And what they did is they also, from a separate source, got latitude and longitude information for the universities and plotted them against each other. This is only one of the many plots they made. And it looks like, no, there actually isn't, which they thought was nice. But once they realized that there isn't a whole lot going on here, they actually went on and wrote some code that iterated through all of these university websites. So if you click on all of these links, you get to more information, and they were actually harvest more data and incorporate that into their project as well. So if you're interested in doing an activity like this, I've linked here in the slides to basically the homework assignment I give using this, so you can kind of see how one might structure a web scraping homework assignment. And also, we're not going to go through kind of you running each of these in RStudio Cloud during the session, but I also did create projects in the RStudio Cloud workspace that I shared with you for each of the case studies that we're going through, so you can find the code related to this. And I actually have a paper coming out with the other Mina Doja, on web scraping in the statistics and data science curriculum, where we talk through the details of why we might want to be teaching web scraping within a statistics and data science curriculum, and what are some challenges and opportunities associated with that. The next case study is about the fisheries of the world, and I don't know if you recognize this, but this is from the pictures from my hometown, Istanbul. And this was a visualization that was given to me. And actually, this was given to me as an Excel file, and I was able to update that with more recent data, because it turns out this is actually a really easy visualization to make with a tool like Excel. But I think we can see a lot of undesirable properties about this visualization. So we start by kind of critiquing this visualization and thinking about how we might want to make it better. And one of the things students quickly land on is, well, we have geographic data here about how much fishing is happening, either from, so the blue and red lines are capture or aquaculture, from capture or fish, farm fishing basically, from countries, but there is no geography that is being presented in this visualization. So how do we go about getting that information in? This is an opportunity to talk about data joins, getting continent information and joining it with your data. When you do join data sources where you have a list of countries and list of anything else, chances are there's going to be a mismatch. The world is not in agreement currently about what constitutes a country. There are considerations around what constitutes borders. So this actually lands us into a nice discussion about data science ethics. And in one case, we are actually teaching them how to recode certain things. So here we're recoding certain countries to particular continents, and we make the decision based on their geography, instead of going into, do we consider this entity a country or not? But I think it is an important consideration that basically whenever you draw a map, you make a political statement, and you should be cognizant of that. Once we do this and we have our data in a format, a tidy format, we can do things like doing country comparisons. So we critique the original plot, improve the data visualization, and we even do a little bit of mapping by introducing the idea of shape files a little bit. Mapping could be its own class as a whole. So, you know, there is only, I would say dipping our toes in mapping would be the right thing to say here. But when you're mapping things like countries, there is our packages that already have these shape files. So it is not as difficult a job as if you were mapping, say, a rural area. And here's an example from one of my student teams, again, from last fall. So they wanted to ask the question, would the outcome of the 2016 US presidential elections been different had Bernie Sanders been the Democratic candidate? And they actually did mapping, and they did regression for predicting what the voting outcome would be like in each county and also by state. And just so you're aware that I'm not actually doctoring these images, I think if you look at these, you'll recognize one thing that's off. The statistical analysis was good, but if we're picking these colors red and blue, I think we would want to flip them around and make Donald Trump the red color and Bernie Sanders the blue color. I think they just went with the default color choices and didn't actually make that connection there. So if you are interested in this sort of improving data visualization type exercises, I've again linked to a lab that we do on this. So that's like a group-based lab that the students work on. The code is in the next project in RStudio Cloud. And I have a sample lecture on this as well. Recently, Maria Tackett and I, for our chance column, taking a chance in the classroom, right? Wrote a piece called From Drab to Fab that goes through a similar activity like this. And there's also good talks about it. One of the ones I really like is by Allison Hill, Take a Sad Plot and Make It Better. So this sort of sequential improvement of visualizations allows students to make critiques and then allows you to kind of respond to that with, and here is how we can do that with the code. And it's a nice way of teaching data visualization with a purpose and kind of a guiding principle in mind. And the last example I'm going to give is actually a very traditional example using spam filters. So we do one lesson on logistic regression in this curriculum. So I'm teaching currently in a 11-week semester, so it's a bit shorter than what I was teaching at Duke. So some of the content from the original design of this course we've cut out, but we still spend a lesson on logistic regression and start to do some prediction. So we have data on one of my collaborators, actually David Diaz's email, and we've encoded certain attributes of 50,000 or so emails. And so we're looking to see whether it was characterized as spam. So first we have a discussion about how do you think spam filters work? What might be some keywords? What might be some other things they could be looking for? But I think more important than fitting that model is that this sort of thing brings about the opportunity to start talking about decision errors, the notion of sensitivity and specificity, and just this intuition around loss functions. And I think this stuff is so important and so relevant, and more important than what actually sensitivity and specificity means, in the sense that like which one is false positive, which one's false negative. But this idea of how do people make decision with data? And is it possible that one's decision might differ from the others based on what we are calling loss functions here? So using what they've learned on logistic regression, one of the teams decided to see, is it possible to predict the year a song made the top tracks playlist based on its metadata? So if you listen to Spotify at all, that's actually pretty good at predicting what you might like. And it does it based on some of these variables that they categorize the songs on, things like danceability, instrumentalness, so on and so forth. So this team wanted to see between years 2017 and 2018, at the time, those were the two most recent years, what were the songs that made the top tracks? Now, you can imagine that this wasn't actually the most fruitful exercise, because between 2017 and 2018, the music hasn't changed that much. If we're doing 1960s and 2000s, I think so. However, one of the things that both the team and during the presentation, the students recognized is that one of the artists that is coming up to be uniquely 2018 is XXXTentacion, and there's a reason for that. The artist was killed by a gunshot that year, and that was a big deal, and it made the news, and it actually gave a boost to his music, as often happens with artists. And so it didn't actually necessarily sound like music that was made around those, that was so popular at the time, but there was another reason it did make the top tracks playlist, and that it didn't actually show up in 2017. So when students start recognizing that a piece of knowledge that they might have, some intuition they might have about the data, is actually being presented in the modeling results, it gives them a reason to, you know, trust the modeling process, which I think is was a nice takeaway. I have a lecture on logistic regression, like how we introduce it and the depth we go into, given that we don't end up being able to spend a whole lot of time on it, if that would be useful to see. And I put the code from that on RStudio Cloud as well. And we have a nice logistic regression example in Open Intro Statistics 4th edition, where we do this based on randomized control trial data on discrimination on job application evaluation. That might be of interest to those wanting to teach logistic regression. So I've went through the case study. So let me say a little bit about pedagogy now. So how do we make this happen? And I'm not going to go through all the pedagogical aspects, but I want to highlight 4 things. One of the things is, I think working in teams is incredibly important. For data science, but for many things as well. So I think where possible, it's important for us to have students working in teams. And I think at least for the upcoming school year, this is going to be a big challenge, because we won't really have the students on campus probably. And even if we did, chances are they're going to need to be physically distancing. So working in teams is going to look very difficult, very different. That being said, I think there's a lot of good tools for working in teams online, and I hope that we'll be able to leverage those. So the students work on weekly labs in teams, and they also do periodic team evaluations where they rate each other, both on a scale, but also more importantly, they write some text about it that gets shared with each other, that I think provides both for the instructor, it's useful to see who might not be contributing as much, to see if that student actually needs a little bit of additional support at the time, but also for making sure that they are communicating with each other in a healthy way. And ultimately, all of this doing weekly teamwork leads to this team project at the end. And by that time, the nice thing is students know each other. They know each other's schedule. They hopefully have developed a dialogue and a workflow between themselves, and have gotten to know each other in a way that maybe they know what is common among their interests. So when it comes to picking a project topic, a topic of their own choice, they can find something that is of interest to most of them. Another thing is peer feedback. So this is different than evaluating your teammate to say, have they been contributing or not? But this is more about actually using students to give feedback to each other's work, written work. So, so far I've used this minimally, but the experience has been very positive. So we've used peer feedback on the project proposal stage, where teams have written project proposals and other teams have given feedback to them. And the nice thing is, I think there are 2 things that's super nice about using peer feedback. The first one, I think the more important one, is that they get to learn from each other. If there's something good, that becomes contagious in a good way. And if there is something that is not as good, that tends to not become as contagious, but instead actually maybe makes life painful for the person giving feedback, but in a way that they learn from it. I think, for example, there's nothing like teaching about the importance of reproducibility than being put in a situation where you have to reproduce somebody else's assignment as your homework assignment, and now you're seeing that, well, they haven't put the necessary files here and I can't reproduce it. That's when you really become aware that, well, okay, I guess reproducibility is important. The other benefit of peer feedback is it gives you more bodies to give feedback. So we actually, we had a session on automated grading earlier. So I think this is another way of expanding your human resources in the course without actually adding human bodies on the teaching staff side. Another thing that we do is this idea of a minute paper. So they have these weekly online quizzes. And at the end of each one of these, there's a brief reflection on the week's material. So it looks like this. And if you look at the very end, it says after you've done these 10 questions, write about 1 or 2 questions you didn't get initially, but were able to solve after a few tries. What was difficult about them, or what did you ultimately learn? Or if you got every single question correct on the first try, write 1 question you would still like clarified. Now, this is not that novel a thing. You know, weekly quizzes, types of things have been around forever. And we as instructors usually look at what questions students missed, and then can usually hypothesize about why they missed it. But if you actually give the students an opportunity to write down why they think they missed it, and then what I usually do with this free-form text answer is grab those and just like make, very crude text analysis things of like which words appear most often. It really gives you a sense of what happened last week that was confusing, that allows you to maybe start your next week with in your lecture. And finally, make room for, use assignments that make room for some creativity. I think it's a really empowering thing that they can be creative with data, and we should try to allow them to do that as much as possible. So one way of doing this is having a final project that's completely open-ended. So you can see that my project assignment just says, pick a data set, any data set, and do something with it. There's more to it, obviously, because you can't just give instructions like that and let students loose, because that would actually probably create more anxiety than you intended. But it does say, like in a nutshell, this is what we want you to do. I think if you're in a situation where this is feasible, you should have an open-ended project for your course. But sometimes from a staffing and grading perspective, this may be very, very difficult to do if you're teaching a huge class and you won't be able to actually grade that much open-ended work. So sometimes you can actually do this in a smaller form. So here's an activity that I actually stumbled upon on Twitter that said, take this ggplot, make it ugly. So instead of improving it, go the other way. And it turns out people love making things ugly because, they get into this race of like, no, mine is uglier. So here's one example. This student wanted to make it look like a football stadium, and they did. So I said I am in the UK right now. I'm actually in Scotland. And if you've ever been to Scotland before, you probably know 2 things, the tartans and iron brew. And iron brew is this drink that is this color. So this student wanted to make the ggplot to look like an iron brew tartan. Now, what did they learn in this process? Right, it was fun for them is what they said. But one of the things they learned is they learned how to change background and the guiding lines of a ggplot. I mean, how many of you know how to do this? I'm sure many of you do, but how many of you have done this early in playing around with ggplot? And we were able to do this without devoting any class time to it. So they at least learned that, yes, I don't have to stick to the defaults. I can change them. Hopefully I won't make them this ugly, but now I'm empowered to actually play around with my visualizations even more. And finally, let's talk a bit about how do we make all of this happen. Well, we talked about RStudio Cloud. So the idea is get students working and playing with data and writing R code, which is what we're trying to teach them here, as opposed to teaching them full-on software engineering, which would be another interesting class to teach, but there's simply not enough time in an intro data science course where we're also teaching them statistics as well. So try to take away some of the hurdle of installation and getting started with cloud-based access to RStudio. And also, I said we use GitHub for students, so everything is version controlled for them. And that means I, as the instructor, have to create repositories on GitHub for every assignment and every student. So the number, I think by the end of the semester, is like thousands of repositories in our organization, which if I had to point and click around and do it would be really difficult. So we have a package called GH class that allows you to do that. And we also use GitHub Actions to give some automated feedback to students. So far, the automated feedback is for formative stuff. So I'll give you one example of doing, doing styling. So here you can see the red side is what the student wrote, and this is a real example, and the green side is what the styler code is telling them these are things I want to change, for example. And so this takes me no time to give them this sort of feedback, and they can actually go and make these corrections until the styler is not doing any further corrections for them. Another thing is I talked about peer review. So one of the things that's hard about peer review is getting all the submissions from your students, anonymizing them, randomly assigning them to people, getting those back, giving it back to the students, and then peer review literature says it's also good for students to reflect on the review they got. So there's a lot of like moving of pieces around that as the number of students grows becomes a hassle. So the GH class package actually has a set of peer functions that allows you to move these files around that, you know, allows you to automate this process, basically. I will say that one of the things we ran into is that the GitHub API turns out has some limits on data sizes. So that's something I'll be working on fixing over the summer. But for many of the students, the data they were working with was nowhere close to the size of that limit. So for most students, the functions worked perfectly well. So I talked about three things, and I'll mention the last thing that's kind of, I think, important when we're working in this in the space of data science is the idea of openness. Not all data science work is open, but lots of good data science work is open. So in the spirit of that, all of the materials that I talked about for the course that I was teaching here in Edinburgh is at this website, introds.org. So if you want to see like how you lay this out for an 11-week semester and get kind of ideas for assignments or whatever, that's all openly licensed. And also I maintain this project called Data Science in a Box that's hopefully going over a refresh over the summer that has more of a 15-week curriculum of this. The infrastructure bit is something I kind of glossed over more like kind of through words at you. But you know, if you're thinking, how would I set up my course to run on RStudio Cloud and with Git, we certainly didn't get into enough details about how to do that in the time we have allotted. But I gave a workshop, like a 2-day workshop on this back in January at RStudio Conf, and the materials from that are openly available as well if you're interested in browsing through those. The slides are on the link at the yellow banner. And as I mentioned, all those case studies, I did put them on RStudio Cloud. If you want to just give them a quick try, I think that's great. But if you're interested in getting the source code, they're also on the GitHub repository for the Preparing to Teach workshop that this is also a part of. So you're welcome to just get the source files as well. So that's it for me in terms of the slides, but I'd be happy to answer any questions if there are.
Thank you, Mina. We do have a question from early in your presentation about there's a trade-off between teaching programming ground up from the fundamentals and starting with tidyverse, which is very high level. How do you weigh the advantages, disadvantages of each for intro stats?
So I would say that there's actually, so the whole of the tidyverse, so that's 8 core packages plus many other surrounding packages. The whole of those packages certainly would make for way more than a semester-long curriculum that is like advanced computing almost. However, certain components of the tidyverse are actually designed with the beginner in mind. And so when I say we're teaching with the tidyverse, really what I mean is we teach bits and pieces of the tidyverse that enables students to go through this data science cycle as easily as possible. And so I would say that for both intro statistics and intro data science, that is the way to get started with coding in R because of a few reasons. The consistent API between the packages makes it such that when you go from you know, doing something like working with factors to working with character strings, the functions don't all of a sudden, you know, the argument orders aren't changed and stuff like that. So I think that consistency is nice. Another thing I will say for the tidyverse is I think the function names they sound like the English names. So if you are teaching within a curriculum where it's in English, I think that's correct, except for the word mutate. I don't think I've ever said mutate this many times before dplyr came about. But aside from that, I think the words are very self-descriptive. And the nice thing is, once students learn that sort of syntax, for example, let's take dplyr, if at a later time they're going to learn about databases, which if they want to be a data scientist, they should, that is kind of that switchover is really enabled by the consistency of the language.
Excellent. I'm checking our chat here.
There seems to be
Here we
one
go.
more question.
In terms of teaching thinking statistically, do you find that students are able to take on critical mindsets through this data science approach? Or are there things that still need to be addressed directly, such as how to read the p-value, etc.? Is this a follow-up track?
Right. So I will mention one thing about how to read the p-value. So we try to downplay the p-value as much as possible, not because I wouldn't say in this day and age we should not mention p-values at all, because I think you run the risk of then somebody misinterpreting them as well. I think we should be teaching them how to interpret them appropriately. However, when they're first being introduced to inference isn't just testing. And I think the estimation part of inference is very, very interesting and important, because it makes it a lot easier to then start talking about effect sizes. So we focus on building confidence intervals as opposed to doing hypothesis testing to begin with. Ultimately, should they learn how to read p-values? Yes. And they do get exposed to it a little bit in this course. But the idea is, if they are going to be statisticians, they most certainly will learn that in a later course. And if they are interested at the end of this course to come back and take something like a second course in statistics, they're going to see that. So my goal with this is, let's teach them the core skills for doing data science and making understanding their data and being able to ask good questions, and introduce them to statistical inference, but not necessarily equip them with everything they need to be able to complete statistical inference.
Great, thank you. We have another question. What kind of time commitment do you think your curriculum would take compared to a traditional one?
Well, if it had to take a lot more than a traditional one, I'm sure the students would not be taking the course. So I can give some, this is a hard question to answer. So the curriculum is designed so that each week students should be engaging with the material for about 10 hours a week, including class time, because that's what usually a full credit course is. When we ask students on course evaluations at the end of the semester how much time they spent, that tends to be more on the hour of like 5 to 6 hours or so. So I'm not really sure that, I don't know if it compares as less or more. I've certainly taught more traditional courses that had just as much, homework and stuff. I think one of the things that's challenging in terms of a time commitment is the very beginning of this class. And one of the reasons why it's challenging is because it is offered by a stats faculty member within a stats curriculum. And students in the first couple of weeks sometimes say, even though they have chosen to sign up for a data science course, I didn't realize we were going to do so much computing. Is this a computer science course? And then, you know, they kind of get into the groove of doing the computing to be able to reason around data. And I think that feeling settles down a bit at the beginning. But I think initially for those who are new to computing, inevitably it does seem more strange than the types of things they've done in high school. I think are you muted or am I not hearing you? Second.
How about now?
I can hear you now.
Now we go. How about adapting these materials for remote teaching?
That's a really good question. So the plan is this, that so the course is designed as weekly modules anyway. So we would still have the lab component weekly with an optional synchronous component to it, but I think it will have to be optional because students will be scattered all over the world. And so time zones are hard. So the goal is, because it's a large class, we can afford to run it over multiple times a week. And hopefully people will file in according to their time zones. And the nice thing about the tooling is that the work is done on GitHub as GitHub repositories that were collaborative anyway, so that you don't need to be in person with somebody else to be able to be collaborating on GitHub. So the tooling will hold up, and the students will be, I think, conversing more over either GitHub issues or something else for their teamwork. And I think we'll put them into teams according to their time zones at least, which I think has other downsides, but at least will enable some communication. Otherwise, the lectures are pre-recorded videos. However, one of the things that I am planning to do is, I think pre-recorded video has the, you know, the downside of, I think, feeling like it's not actually responding to what the students are like thinking about and learning at that time. So using those weekly minute paper things to actually develop like a weekly 15-minute State of the Union address that is just like shot very low budget at the time, you know, that would be the first 15 minutes of my Monday lecture anyway, and doing those a little bit more real time throughout the semester to at least correspond to kind of where the students are at. Aside from that, I don't know. We'll see.
I don't want to forget to make sure that you see that there's a number of comments about being thankful for your wonderful materials and appreciating that you're sharing that
Thank
stuff. Question about how big are your classes?
So far I've taught this with 100 students at a time. I think the cap we're putting on it, sorry, 120. I think we had the largest class at Duke for this. We had put a cap on that. Next year, we're putting a cap of 400. So now that we're not bound by physical spaces. So one of the things has been that for the computing labs, if you're not at an institution where you can require students to have computers in their first year, as in the institution doesn't have a you know, an opportunity for students who don't own a laptop to get one, then you have to teach this in a computer lab, even though we're not actually tied to those computers from a software perspective. So far the limits has been set by the physical space. So with remote learning, we don't have that. So we'll see how crazy it gets.
So is your course embedded in the entire curriculum in the sense that you know or facilitate that staff colleagues ask students to implement the notions and procedures that they learned in your course?
So I think this was certainly the case at Duke, and actually some of the changes to the second and third courses there have happened knowing that many students are coming in through this curriculum. I couldn't necessarily say that right now for the institution that I'm in because it's the first year I'm teaching it here. So it's a new course here. And usually I think for a course to be embedded in a curriculum like that, a new course like this, it takes a little bit of time. But I think, so we are to see once these students that took this course go into their Stat 2 course, how they are engaging with that material and whether changes should either need to be made or should be made in some way. But it has certainly informed the curriculum and, nudged things a certain way at Duke.
All right. Do you experience large variation in engagement of students in the projects based on ability or interest? In mandatory courses, we struggle with many students who are actively disinterested.
So this is not a mandatory course, so it's possible that there's a little bit of a benefit from that. But obviously, yes, I mean, there's definitely variation in engagement. And I think there are usually two reasons for it. One of them is kind of students losing the thread at some point throughout the curriculum. And however much you want to, reach out to them, especially as the class sizes get larger, it becomes harder to catch these early and be able to provide kind of one-on-one guidance to them. Our peer evaluations actually have been really good for keeping students honest in a way, because I think they actually feel more wanting to respond positively to their peers' feedback of like, why don't you show up to lab on time, than me saying the same thing. The other thing is, so that's a subset of the students. I think the other bit is a group of students, sometimes just like decide this is actually not what I wanted to do in my life. And I'm not really sure what you can do with that. I think one of the things that we do try to do is when we have these teams, there are 4 people. So when it's too big, I think it's too hard for them to manage collaborating and manage schedules and stuff like that. But I think really small teams, if you have one student who loses interest, makes it really difficult for the rest of the team. So giving your teams a little bit of breathing room by adding an additional person helps.
So I think this may be our last question. Do you feel that we're now in an era where all intro stats classes should have these data science components included, like data visualization, web scraping, etc.?
Data visualization, yes, I would say so. And I think when I say, obviously a histogram is a data visualization, a box plot is entirely valid ones, but I think we can go beyond those. And I think that is true whatever software you use, whether that's a programming language or an online applet or anything. So I think data visualization, absolutely, because if we go back to the GAISE guidelines, that is a fantastic way to start thinking about multivariate relationships without having to get into the modeling aspects, which I'm saying having to, it's not a bad thing. It's just I am recognizing that in some curricula that may not be feasible. You might have a 6-week summer course, or you might have a subset of like a particular audience that you're geared to where that's simply not going to be part of the kind of curriculum. So I think data visualization, absolutely. Web scraping, I think there's a lot of value to teaching web scraping. So in the paper that I mentioned that we wrote, we tried to kind of think about what levels of web scraping might be useful to infuse into different levels of courses. So the full gamut that I talked about probably belongs in a course where computing was the main kind of focus. Otherwise, teaching iteration and mapping and stuff like that would be a little bit much, perhaps, for a more traditional introductory statistics course. But I think there's the idea that you can get data from the web and you don't have to do it by manually typing it in is a useful thing to get across to our students. So I think, yes, they should have these components. The level to which they will have them, I kind of want to say time will tell, and I think our students' interest will tell as well. And also how high school changes, obviously.
Mm-hmm. Well, you have some more thanks, including specifically from a mathematician who is teaching intro stats and a user of the Open Intro book. It's 5:15. It's time for us to move on to the poster session and wrap up our day. If you're interested in continuing this conversation with Mina and Ulrike, we I'm putting it in the chat box. I don't know if I can do 2 things at once. an opportunity for you to vote on Friday's hot topic session for Wednesday. So you can tell us what you want to talk about on Friday that comes out of today's sessions. And this form gives you the list of everything that happened today. And you could tell us what you'd like to talk more about on Friday through that way. Don't forget our Twitter hashtag, eCOTS 2020, the Slack channel, and Facebook communities, all places that you can continue the conversation with your peers. Thank you so much for a great day today.